Today, we will start discussing about a topic which I was mentioning in the passing for a long time, that is hardware software partitioning. Now, in the last example that we have done, we have seen that we have arrived at that design in an iterative way, right. So, what we did is we tried with different options, started with only software option and then found that the constraints were not met. Then we gradually shifted towards hardware for some specific parts and also did some software adjustments, like instead of fixed point, instead of floating point going to fixed point, and iteratively checking whether the constraints are met. Now, we can also look at it a little more systematically also. One is iteratively, but that is very effective and mostly done, but there are some algorithms for doing that too, right. So, before we go to hardware software partitioning, we know what it is, that we start with a specification and then during the design phase I decide which parts will be in hardware and which parts will be in software, right. Now, along with the specification I have got some constraints, and the constraints are of two types. One is optimizing constraints and the other I call it satisficing constraint. By that what I mean is that it is enough to be able to satisfy these constraints, we need not optimize it. Say for example, we are given a time constraint that the entire thing will have to be done within some stipulated time. Now, that we have to satisfy, we need not optimize on the time, but while doing that, suppose the statement is that we will have to satisfy the timing constraint with minimal area possible, right. Then we have to try to optimize on the area. Okay. So, that is why there are two types of constraints. One is now, how do we make a decision as to which one will be done in hardware and which one will be done in software? Obviously, the advantage of implementations using hardware is that they will be faster, and on the con side it is that they will be more expensive, more power consuming maybe at times, though not always, since they will be faster, the energy may be saved, okay. The time to market will be higher, etc. And whenever now this specification is coming to us in the form of a say control and data flow graph that we have seen already when we studied scheduling, right. Now, when we studied scheduling, we were given a control and data flow graph and we decided on, say for example, let me recollect the square root approximation algorithm. So, it was something like this, that we had an absolute computation for A, we had an absolute computation for B, and then there was a max computation there was a mean computation, so and so forth, right. So, we proceeded in this way. So, in that way there was a graph and we had the option of selecting the absolute computation either by hardware or by software. Okay. Now, there are several issues here regarding, say for example, in say one of these operations are something like delay. Say somewhere in some hypothetical graph we have some delay here. Is it readable? Otherwise, I am just showing it separately, that in my graph somewhere I have got a delay. Now, this delay can be done by software. I can just put a software loop, wait loop, or I can put a timer. So, I have got two options of doing this. So, depending on whether I want to do it using software or hardware, my cost will vary. But suppose it was something like this, that here at the same step, in the same control step through another path, I am going to do some multiplication. And suppose I decide that this multiplication will be done by the processor. As I decide that this multiplication will be done by the processor, and since I am in the uniprocessor environment, that is my assumption that I am doing one processor, then this delay cannot be done in software. Therefore, that is ruled out. Vice versa also, that if I commit a priori that this delay will be done in software, then this multiplication cannot be done in hardware, unless I change the schedule and delay this delay from this control step to some other control step, or delay this multiplication to some other control step. Therefore, my hardware software partitioning decision is also integrally related with the scheduling that we do. Now, when we do hardware software partitioning, we will have two things. One is the list of functional elements, list of functional elements means the operators. All right, the operators themselves, like max, mean, multiplication, division, square root, whatever. That is one. Another one is list of implementations available. Now, what do I mean by available implementations? If you think of a laboratory scenario, whatever components are there in your shelves, which you can use, right, or in a high level scenario, advanced scenario, all the different cores that you have which are available, right, the VHDL definitions of whichever components, that is, those are my design library. So, this is actually giving me a design library. Now, in the design library, I can have 4 types of implementations. I can have 4 types of implementations. What are the 4 types of implementations? One can be that it will be a pure software implementation. So, somewhere it will take some input, we will do some software computation and will come out. And along with this implementations, the cost and other parameters will be stored in the design library. For example, a delay can be implemented using software. Okay. It can be purely a hardware implementation. For example, say I want to do the analog to digital conversion, using a chip. I forgot the names of the chips, but it is something like, if I recollect, ADC 801 or something like that, 808. So, might be ADC 808. So, so some chip is there, and that chip is sufficient to do the analog to digital conversion. Okay. And this one, this ADC hardware chip is doing it using a flash method, right. Besides, I can have an implementation where I am doing a software implementation, but for that I need some hardware support. For example, if I want to do ADC using successive approximation method, so this one can be done using successive approximation, but for that ADC with successive approximation, but for that I need the support of the hardware. I need a comparator, hardware comparator, and I also need a DAC, right, digital to analog converter. So, as soon as I decide that okay, this ADC part I will be doing by software. So, what did you have? You had in your task graph the number of nodes coming in, and here somewhere you have come to a point where you need to do ADC. And this ADC now is a decision point. You want to weigh your options and want to see if I want to do, if I can do this ADC using software. Maybe you are very well comfortably placed with regard to time constraint. So, you can opt for a low cost solution. So, you try to do this using this, but as soon as you do that, you will need some other hardware to be incorporated. Therefore, the implementation list that was there, I was talking of the list of implementations available, that the list of implementations available must take note of this fact, the implementation of ADC using software method is successive approximation, additional hardware required of this. Okay. So, when you compute the cost, you have to take into account that. The other option that can be is, suppose I want to implement something with a hardware. Now, I want to, this hardware is basically I want to implement a timer, and for the timer say I select for example, Intel's 8053. I hope that is a timer, if my memory does not betray me. So, it is a timer, all right, and the timer being a programmable timer will require some software support. Okay. What sort of software support? There should be some initialization. This timer has to be initialized, and maybe this timer will have to be, it is a counter, say it is acting as a counter. So, after some point maybe the software will give it a stop signal, and then this will give me the data. So, these are coming from the software, all right. Therefore, or say for example, a port or an interrupt controller, that is a hardware, an interrupt controller is a hardware, but you need a programming to do that. So, therefore, there will be some software overhead or software cost for that hardware itself. So, there are cases where it is not just hardware or just software, but often it is a combination. Okay. So, we will have again what I said, we will have a design library. Now, how can we define the hardware software partitioning? Let us look at a formal way of looking at it. We can define the hardware software partitioning problem as follows. That given say f is the set of functional elements, Fe means functional elements, okay, in a CDFG. We know what is a control and data flow graph, right. And I is a set of I sub I, where I sub I is the set of possible implementations of a particular function of f I, all right. And also I is a subset of I H S, which is the hardware implementations union the software implementations. Okay. Now, whenever I take a hardware implementation, I have to look at whether this hardware implementation requires some additional software and vice versa for the software. All right. IHS is the library of available implementations. All right. Okay. Now, given this definition, is the definition clear? IHS is what? IH is the set of all hardware implementation and IS is the set of all software implementations. And there is T, which is the set of end to end timing constraints defined over parts of CDFG. Now, when I write parts of CDFG, what do I mean? I mean that there may be cases that I have got a CDFG it is a data flow graph coming to be something like that, and well this goes to something else, and then this one comes here and something else comes here and I go up like this. Now, it can be that the timing constraint from this operation to this operation is T 1. I can also specify that after this is done, the completion of this must be done in T 2. I can have multiple timing constraints attached, right. That is why I am saying that it is part on the part of CDFG. So, given this, let us look at once again, given the set of functional elements and the set of implementations, our task, hardware software partitioning task, is to determine an allocation I j belonging to I for every f I, all right, and a schedule of these allocations such that T is satisfied and cost of I j is minimized. Okay. So, that is my hardware software partitioning problem. Okay. So, we have seen what is IIJ. IIJ is a set of implementations. We have to find an allocation that a particular FEI is being given an allocation j, all right, and that is among all the available implementations, and that can mean hardware or that can mean software. So, and I have to satisfy the time and have to optimize the cost, all right. So, that is the hardware software partitioning problem. Now, in computer science, you have come across such problems often, different varieties of optimization problem. Okay. Now, historically, if we look at the hardware software partitioning problem has been addressed in a simpler way. The way we have seen in the digital camera example, first what was done is you try for all software solution. Okay. So, and then you find whether the constraints are satisfied. If not, then look at the hotspots, find hotspots, and move them to hardware. Okay. Now, obviously, here also you have to have a decision making. So, that is an iterative way of doing it, the way we did for digital camera example. The other option is obviously a dual of this. You try for all hardware solution. Okay. In that case, what will happen? You will be able to meet the timing, but maybe the cost is we are not actually taking the time to market so much in consideration in this discussion, but the cost will be high, the power or all those things can be violated. Then we try to see which are the places where I can soften the speed and then move to software in parts. So, these are different ways of doing it. That is another factor. The question is whether flexibility should play a role. Yes, that is coming as a non-functional requirement at the very beginning, and that can serve as an additional constraint, that I want to have the option of adding some features. Therefore, a priori when I was saying that I am given the set of functional elements, the constraints can also dictate that this parts tasks will have to be done in software, or this things will have to be done in hardware. So, if that is given, then that is already determined, you have to play with the other things. Okay. So, in that case, in our allocation, in our definition, this allocation, some of the allocations are already done. So, I am left with another set for doing the allocation. All right. That is a very good issue, that especially in the mobile phone and all those, we always look at the scope of adding features, so that we can be competitive in the market. Now, so these are the two things, and the other way is some integrated approach. Now, for optimization. Now, there are several approaches of carrying out optimization. Now, this one, the hardware software partitioning problem that we have defined, the way we have defined, maps very well to a well known computer science problem, which is the consistent labeling problem. For those of you who have done that, it may be familiar to you. This will also become a consistent labeling problem, and the standard methods of consistent labeling may be attempted to be applied. I will show some difference with that consistent labeling problem, but before the showing the difference, you just keep in mind this definition, that F is a set of functional elements, I is a set of implementations. Just to give you a notion, I can try to explain it in the form of a bipartite graph also, that I have got some functional elements which are being shown as circular nodes, and there are some implementations which are shown as rectangular blocks. All right. Now, we have got the implementation list. So, these are the implementations and these are the functional elements. Now, the implementation list may say that okay, this functional element 1 can be achieved with A. Similarly, C can also achieve 1, whether they are hardware or software, that part I am not coming to right now. 2 can be achieved by A or by B. 3 can be achieved by D only, say, and 4 can be achieved by C and E, suppose. And I have to find and along with that there are some constraints also given. The cost constraint for each coloring or each mapping, I have to incur some costs, and the cost constraints are there. Each of these functional elements have got time and area cost. So, the task is to find a consistent labeling of the functional elements with the available implementations, such that all the constraints are met. That is consistent labeling. Okay. And so, let us define it, the CLP. Where in CLP we have got a set of variables V, a set of vertices, okay, and 2 a domain, that is a set of values. Domain is a set of values ui such that each variable vi belonging to V may be labeled by uij selected from ui. all right. Then I will select from the domain some value for mapping it to this variable. Two types of, now when I do this, along with that I add, there will be some optimizing cost, okay, which I can say opt cost and satisficing cost. I call it sat cost. And also there can be a cumulative cost like the time and all those. So, now if I have this and this, I can straightway find a mapping between the CLP problem and the hardware software partitioning problem. What is the mapping? What is the mapping? The mapping is this V is just mapping to my set F, the set of functional elements, right. The UI here is mapping to the set, say what, Ij, which will have a particular implementation and a step, right. Implementation Ij and step j. What did I denote it with this here? The ultimately we are determining the Ij, right. That is coming as Uij. The other costs we have already seen. Therefore, we can apply the methods of consistent labeling problem to solve the hardware software partitioning problem. But there is a major difference from the consistent labeling problem and the hardware software partitioning problem. What is that? In the consistent labeling problem, the set of variables are static, the set of variables are known a priori. But in our case, in hardware software partitioning, they are not known a priori. They are known a priori, but sometimes what happens, as soon as you select a particular implementation, then just as we had done few moments earlier, whenever I select an element that will be implemented using a software, and for that we need some hardware, then I have to add that hardware to my list of variables, because for that hardware I will be needing some other implementation. So, the set of variables are not constant. Okay. Now, I am not going into the details of the algorithms, but so one thing is that, as we have done in the digital camera example, you can start with all software solution and move to hardware, or you can do start with hardware and move to software, or you can try to apply the consistent labeling problems type of solution, and the solutions are actually done through different means. For any of these, you can do it with dynamic programming, you can do with branch and bound actually, and through heuristic search. So, you can do branch and bound, heuristic search, or greedy. Why am I leaving out greedy? Let us start with that first, which often, say for example, the ones that I was talking about, that put every solution in hardware and then gradually move to software, that is also greedy. Move everything to software, that is also greedy. So, either you can do, and as you get this, so what will happen is, you will have a search space with all possible paths that can be traversed in this search space, right. You understand that this is a tree sort of thing, where you can follow different solution paths, right, as you go on doing the allocations. Now, this you can do with a greedy method, you can do with branch and bound, or you can apply suitable heuristics for doing that. Okay. That is one way of doing, but while doing this we have got the CLP issue plus we have got the additional variable scenario. You have to add the variables and accordingly. So, what will happen is the variable list that you will have to continually update at every step of allocation. So, what will the algorithm will look like? So, I will just say in brief how what the algorithm may possibly look like. It will be, you will have some implementation list. Okay. And you have got the functional elements. All right. So, maybe heuristically you will have to first order the implementation list, maybe based on their cost, maybe their reuse potential. As you do it, this is something I forgot to mention. We look at the cost and also there is another issue of looking at the reuse potential. For example, if I select an ALU, it will be expensive maybe, but it can be reused for so many functional elements, to cover so many functional elements. So, its cost should be compensated for by its reuse potential. So, accordingly we order the implementation list and then select from the list for every Fi, for some Fi, some Fe, some functional element, and see what first we check any additional elements required. If so, then you will have to add to the implementation list, right. If yes, update functional elements, because you will need more functional elements to do, and then compute cost. You go on computing the cost till now and check whether that cost has violated the ultimate cost. Now, and this will be done absolutely heuristically, and you will have to see. So, usually what the problem that occurs in this sort of solution for any CLP solution or for many of the AI search solutions is that the search space is very large. So, you have to do some look ahead and do some pruning, just like branch and bound. You see that if I make this selection, if I follow this particular path, then I am already exceeding my cost. So, there is no point proceeding in that path any further, and so I will select the other paths. In that way, different algorithms can be applied once we formulate the hardware software partitioning problem in a suitable way, as we have done today. Another option, I will just mention it, and another one that I will be just mentioning is a genetic algorithm has also been applied very successfully for hardware software partitioning. What is done in that case is that, as you know, genetic algorithm will have different chromosomes. So, I will have a list of chromosomes, and each chromosome will consist of a number of genes. So, whatever this is my list of all possible functional elements, and I will have for each possible functional element, I will have a gene code of particular length L, say, all right, and I associate some particular implementation with this, all right. Some particular implementation, say for example, 0 1 1 or 0 1 0. In that way, I form the entire bit string. Now, this is one solution. There will be another solution in this way. So, there will be a set of population, and then we take recourse to the crossover functions, by which we take one such chromosome, another such chromosome, and have a crossover and get a new solution. For each of them, we try to find out the fitness function. We will try to see if we can look at it in a little more detail.